add or subtract, it's much harder to compare the relative importance to multiply. Factors to multiply. So when we take the logarithm, and it's n log t minus e over r t. So as a result, now I have these two factors. When I have these two terms, what originally were two factors multiplying each other, which are hard to compare, I have now as terms that are being essentially subtracted or added one to the other. And then it's easy to see if one is big and the other one is small. It's easy to see that this is So in general, it's much easier to compare terms that you add than factors that you multiply, as far as they're important. So whenever you want to compare things like that, you try to get them with the things that you add, as opposed to things you multiply. And that comes up in statistical mechanics as well. We frequently do things like that in many subjects where you have factors and you want to see which are important.
The method of stoichiometric ratios. When we put the ratio of, we have, let's say, CA naught, how you had in the example in the last lecture, over CB naught, you have is equal to alpha over beta, right? I'm looking at this here. Alpha and beta are...
Remember, I choose CA naught and CB naught.
Oh, that's what I was going to say.
I choose them. Alpha and beta are stoichiometric ratios that I determine from the experiment.
So you
and then when I set up a new experiment to use the method of stoichiometric ratios, I set up the experiment, I choose the initial concentration. And the whole trick in that method is to choose the initial concentrations in the right ratio.
The set of rules that you listed last class that includes to non-elementary reactions, any of them are not satisfied, it automatically makes the reaction non-elementary.
Right. Other questions? Any other questions?
But you mentioned alpha and beta is from the experimental concept.
The stoichiometric coefficients from the experiment. Other questions? Okay, if you remember at the end of the last hour, we mentioned that in order to, how do we investigate a mechanism? By the way, what is a mechanism?
Set of elementary.
Wait.
It's a set of elementary reactions that describe the kinetics.
It's a set of elementary reactions that we hope will describe the kinetics. And right now, we're using a batch reactor. What does a batch reactor mean? A batch reactor means at t is equal to, before t is equal to 0, you put all the reactants in, and then you close the reactor. No inlet, no outlet. No in, no out. And you just view what's going on. You view what's going on by looking at the concentrations as a function of time. And using that information, we try to determine a mechanism that describes the kinetics. Notice I say a mechanism, not the mechanism. What's the difference between saying a mechanism and the mechanism in English? That's not what I mean. We have no idea if there's a unique mechanism. Just because I find a mechanism that works doesn't mean there isn't some other mechanism that also describes the data. So I may have more than one mechanism that equally well describes the limited amount of data that I have. If I find two of them that describe the data that I have, then what I might try to do is that from looking at those two mechanisms, I might try to devise a new experiment to distinguish between them. But generally, I have a finite amount of data, and there may be many mechanisms that work for that amount of data. Right now, we're just looking for one. We might find more than one. So let's go ahead and we use mass action. We use mass action kinetics and the pseudo steady state approximation in order, as tools, to try to do this. And remember, the technique we had was we collect data, we guess a mechanism. Guess, remember, we guess. hopefully an educated guess, not a random guess. Then what we do is we write out the differential equations. We solve the differential equations. Differential equations of the mechanism. And usually, often that involves the pseudo steady state assumption. And then we compare with experiment.
You also have quasi-steady state.
Yes, pseudo steady state or quasi steady state assumption. Some books say pseudo, some say quasi. Pseudo means false, that's not really steady state. Quasi means almost steady state. Depending on how you look at it, it may be an almost or a pseudo. They're the same thing, different names for the same thing. You compare with experiment, and if that doesn't work, you go back. If it doesn't compare well, you guess again. If it does compare well, then you celebrate. So that's the basic idea. And I just want to emphasize one thing that I'd like to emphasize, one convention that we're using. If we have a mechanism, say alpha A plus beta B, and dot 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 goes to, let's call this alpha 1, beta 1, to alpha 2 A plus beta 2B, plus dot dot dot. So I've got reactants and products. And sometimes you may have the same species on both sides. You may have A plus B goes to 2A. So therefore I'm allowing alphas and betas on both sides. Presumably they're not going to be the same on both sides unless it happens to be a catalyst. So if I have a catalyst, I can have A plus B plus A plus C. But whatever, this is the most general. Then what I do, when I write out the reaction, if I'm writing out RA, the rate of A, using mass action kinetics here, well, remember I said there's an easy way of doing things. You take the concentration on the tail side of the arrow to the power of the stoichiometric coefficient if this is elementary. So if elementary. Then this is CA to the alpha 1, CA to the alpha 1, CB to the beta 1. But then we have a convention, is that the convention is we have a coefficient K, but then we use the stoichiometry in the coefficient. And the stoichiometry is we take the coefficient, since we're looking at A, we take the coefficient of A on the head of the arrow minus the coefficient of A on the tail of the arrow. So we have alpha 2 minus alpha 1. And if you do this, you'll always get the sign right, and you'll always get the coefficient right. So if I were looking at RB, what would the answer be for RB? Why don't we start from the back this time? Let's start in front left. Beta 2 minus beta 1. Okay. Good. So the only thing that changed is the coefficient here. And notice, this automatically takes care of, let's say A is purely a reactant. So that would say alpha 2 is 0, if A is purely a reactant. Then alpha 2 would be 0, I would have a negative coefficient here. A is getting used up. If B is a product, so there's no beta here, but there is beta here, then beta 1 is 0. So then you see that the coefficient is automatically positive. So I don't have to worry about whether it's a reactant or product. As long as I follow this convention, I always get it right. Okay, so let's look at an example. And we'll look at a couple of examples. So I have a problem where I have the stoichiometry. So we're given the stoichiometry from experiment. So this is experimental data. And if you can't read my handwriting, you can just ask. Otherwise, you'll suffer. Plus 1/2 A. And we said last time that there was a pretty good reason why we know that this mechanism, why this reaction is not elementary. Know this way. So don't be surprised if I call it. I did this last time. Because there's a fraction. Now how about if I just multiply by 2? I get rid of the fraction. Then I'll have 2 of this, and 1 of this. Good, good. Molecularity would be greater than 2. So this is clearly not elementary. And here are some data. at short times, meaning when we start the system, then the rate of A2B goes like the concentration of A2B in the first calorie. So it seems to be first order, of course negative. However, at long times, meaning when most of the reactants are used up, then the rate of A2B seems to go like A2B squared. So it starts out looking first order, it ends up looking second order. We also find that the rate of A2B does not seem to be a function of the concentration of AB. It seems to be independent of the concentration of AB. There's no product inhibition. And the other thing we find is that the rate of A2B goes down as the concentration of A2 goes up, but it's not a simple proportionality. So that's some experimental facts. We wanted to come up with some guesses, some mechanisms. So I'm going to propose the first mechanism, and we're going to analyze it together. So we'll go around the room analyzing it. Okay, so let's look at 2A2B goes to A4B2. A4B2 star. And A4B2 star goes to, what am I looking for? 2AB plus A2. So that's my proposed mechanism. I'm going to call this, let's label them, number them. Yeah. Let's call this reaction 1, 2, 3, 4. And this is my guess. And this is my first mechanism guess. So what I'm going to do, what I'd like to do is I'd like to guess, is that A4B2 star? Yes, A4B2 star. Now the reason I put a star there is so you'll know that it's a reactive intermediate to which the pseudo-steady state assumption holds. I'm assuming that A4B2 star is unstable. As soon as it forms, it then decomposes. So let's go ahead and write out the rate of A2B. Now, A2B is involved in which reactions? The first one. Any others? Just the first reaction? Let's go around the room.
Yeah, it's the first one.
That's called the second one. It has a number. First, is it involved in 3 and 4? I don't see any A2B in 3 and 4. Do you? Do you see any A2B here? So it's involved in 1 and 2, but not in 3 and 4. Okay, help me write out the rate of A2B. You have to speak up. You're sitting in the back. I want everyone to hear you. Loud. Well, why don't we do the coefficient last? Which K? 1 or 2? A1. A2B. Good. Now let's do the coefficient. What's the coefficient? What's the coefficient? What's the coefficient? Are we guessing? I want you to go through what is alpha 2, what is alpha 1? And alpha 1? So what is 0 minus 2? Minus 2. See, when you work it out, it's easy. When you just shout out an answer, you get the wrong answer. Okay, how about reaction 2? We'll do the coefficient last. A2. What's the coefficient?
-0.
Anyone awake here? What's the coefficient? Okay, yeah, actually, no, that's all right, 2 minus 0. Sorry, that's correct. 2 minus 0. Minus 0. Okay, so we have that. Now let's notice, in order to solve this, I need to know A4, B2 star. I need to know A4, B2 star. So in order to get that, I need to write out R of A4, B2 star. So let's see what that is. What reactions is A4, B2 star involved in? So
All the reactions.
all of them. So why don't we start with, so I need 4 terms, one for each of the reactions. Why don't we start with one of the first term? Let's do the coefficient last.
So A1, A2B of potential,
I'm sorry, I didn't hear you.
A2B, that's fine. And that would be 0 minus 2,
What power is on the A2B?
2,
2. Important not to leave that out. And the coefficient is
0 minus 2.
A4, B2 star.
Oh, that would be 0. 2.
Remember, you shout out a number, you're going to get it wrong. You need to know alpha 2 and alpha 1. So you should be giving me 2 numbers and a difference. We're looking at A4, B2 star for reaction 1. I want 2 numbers, alpha 1 minus alpha 2. Is that a hard concept? Okay, so I have 1 minus 0. That's what I would like.
Same for the upper one also, right? For A to B, should be 1 minus 0.
Huh?
For rate A to B, for the
The rate of A to B, we look at the coefficient of A to B. It's 0 here, and it's 2 here, 0 minus 2. Now we look at the rate of A4, B2 star.
first expression, second term, the coefficient will be 1 minus 0.
It's 1 minus 0.
For the upper expression.
For this one,
Yeah.
I just went through it, it's 0 minus 2.
No, the second term.
I'm looking at A2B. I look at the coefficient of A2B on head of the arrow minus the tail of the arrow. For reaction 2, the head of the arrow is 2, the tail of the arrow is this side. The coefficient of A2B is 0 there.
For reaction
Second
portions. For A to
You have
B to
P4.
star.
You're looking at this term.
Yeah.
I just did it 3 times. I'll do it a 4th time. We're looking at the rate of A2B. A2B has a coefficient 0 on this side and 2 on this side. For reaction 2, we look at the head of the arrow. It has a 2. Let me make it explicit here. It was 0 A2B. And the tail of the arrow, it's 0. Because I'm looking at A2B, it's 2 minus 0. Where, since I'm looking at A2B, I look at the stoichiometric coefficient of A2B, not the stoichiometric coefficient of A4, B2 star. You understand that? Is that clear? Okay, the undergraduate seems to understand it. Okay, so let's now go to the next term for A4, B2 star. Since we're interested in A4, B2 star, we're looking at the stoichiometric coefficients of A4, B2 star, not anything else. Okay, so this is reaction 1. Now how about reaction 2?
It's concentration of A4, B2 star,
Give me a K first.
K3,
I want reaction 2.
so the K2,
K2. What's the concentration involved?
0, 0 minus
The concentration involved.
concentration of A4, B2 star,
What power?
1,
Good. And now the coefficient.
0 minus
Okay, the coefficient.
1.
0 minus 1. Correct. Thank you. Good. Good. Next, reaction 3.
Plus K3.
So I've got a K3. A4 B2 star. What power?
No power. 1 power to 1.
Power 1. Good. And the coefficient?
And coefficient is 0 minus 1.
Good. Very good. Good job. Reaction 4.
So the constant, I'm sorry, the K, would be K4. Concentration A4,
K4. I always do the concentrations on the tail of the arrow, not the head of the arrow.
so it'd be 0.
I want the concentrations. What concentrations go there?
A4,
No.
it's,
So here I have the arrow. I always start at the tail of it. I always do the concentrations on the tail of the arrow, not the head of the arrow.
So we got K4, concentration of AB squared
AB squared
times the concentration of A squared. We got
A2.
A2.
Okay, now the coefficient.
Coefficient would be.
Now remember A4, B2 star. So its coefficient is 1 here and 0 here.
So 1 minus
1 minus 0. Good. Okay, so now I think I have enough information to solve. Do you understand? So the A4, B2 star is the rate, yes?
Because the first expression, the second one, we have a typo, so I think we need to go to
Typo, I'm not typing.
K4
It's K2. I have a righto, not a typo. A righto. It's a mistake. We'll just call it a mistake. So we had a K2 there. Okay, my mistake. All right, so now let's see, do we have enough information to solve this? First, this is a reactive intermediate. So what is the assumption we're going to make about the reactive intermediate?
Pseudo-state assumption.
No, we're going in order. What is the assumption we're going to make?
It's a pseudo steady state.
It's a pseudo-steady state, meaning what are we going to set this equal to? 0. Why? What's the justification for that? Because teacher said so? What's the justification? It was in the notes last time. If you looked at your notes, you would know it.
Because it's only used up immediately.
It's too fast, it's used up too fast.
It's too fast. It's happening too fast, so therefore,
Therefore, we assume that it's just
It's used up as fast as it's going, so.
because it's used up as quickly as it's formed. So since its time constant is much faster than everything else, it's like the ticks on the elephant. Okay, so now the question is, do we have enough equations? This equation we were missing, we had one unknown. We have two unknowns here, A4B2 star and RA2B, two unknowns. All the other concentrations, this, this, and this, I assume I can measure because they're stable concentrations. So I have two unknowns, and in this equation, this is known, this is known, this is known, this is known. The only thing that's unknown is this, and it's the same unknown as here. So I have two equations, two unknowns I should be able to solve. So let's solve. So the algebra I'm going to do relatively quickly. First, let's notice that both of these coefficients are -1, and they both have the same A4B2 star. So I can factor out A4B2 star. And in fact, since they have -1s, I'm going to bring them to the other side of the equation. So what's left on the right? What's left on the right is K4 with a plus sign, +1, AB squared A2, plus, plus K1 A2B squared. And these two guys went to the other side of the equation. I factored out the A4B2 star, and I was left with a K2 plus K3, which I divide out. So this is A4B2 star. And now I plug in here to see what I get. So I have R of A2B is equal to -2 K1 A2B squared plus 2 K2 over K2 plus K3 K4 AB squared A2 plus K1 A2B squared. And now I want to put the whole thing under a single denominator. So I'm going to multiply and divide this by K2 plus K3. So I multiplied and divided by K2 plus K3, and let's see what I can cancel. Notice that I have a term here, K1 A2B squared K2, with a minus sign, with a minus 2. And here I have a plus 2 K2 K1 A2B squared. So this term, K2 K1 A2B squared, and this term, K2 K1 A2B squared, exactly cancel because they have opposite signs. What am I left with? I'm left with R A2B is equal to twice 2 divided by K2 plus K3 times K2 K4 AB squared, the outside, A2 minus K1 K3 A2B squared. Is that clear? And now let's see how this compares with experiment. The first piece of data that's useful is let's look at data number 3. The rate does not depend on AB. Well, notice this equation depends on AB. In order for this not to depend on AB, either K2 or K4 has to be 0. So let's look at both possibilities, or at either possibility. If either K2 or K4 is 0, then this term will be 0. And then the result will be second order in A2B. So I have fact 3 tells me the product K2 times K4 equals 0. At least one of those is 0. The product is 0. But then that contradicts fact 1, that it looks like first order. This is purely, once you kill this term off, it's second order. It never looks like first order. So then fact 1 is contradicted. So that little X, double X means contradiction. So that tells me that this mechanism cannot describe the data. So I'm going to come up with another mechanism, and we'll try another one. So let's try A2B goes to, let's make sure, goes to AB plus A star. 1, 2. And then A star plus A2B goes to another AB. Just let me finish the sentence. Another AB, another AB plus A2. This equation says for all times, short, long, infinite, it's always second order. This mechanism is always, this particular expression is always second order. So there's no time at which it's not second order. So therefore, I cannot agree with the experiment. So here we have another potential mechanism, mechanism 2. And let's go through and try to analyze that. So again, I want R of A2B. Who was I up to?
So, A2B not in all 4 reactions?
A2B is in all 4 reactions. So I'm going to have 4 reactions. Those are stoichiometric coefficients. We'll do them last. So I'm going to have a reaction 1, a reaction 2, a reaction 3, and a reaction 4. So what comes in here?
The first one is K1, and the first one of A2B, the coefficient is 0 minus 1.
Good.
And the second.
Let's give other people a chance.
Second one is K2 concentration of AB times A star.
Good.
To the first power and the coefficients.
Remember, I'm looking at
One
A2.
minus zero.
One, good. 1 minus 0. Very good. Next.
Second question is A to B.
Wait, there are more concentrations.
Oh, based on
A star. And the coefficient? 0 minus 1. Good. Next. I'm sorry? You can't read my handwriting? Join me.
Keeping late for the lecture, so I'm going to catch up.
Okay. Try to come on time, and coming in late is not an excuse for not knowing what's going on. Coefficient is 1 minus 0.
Concentration
Concentration rate. Good. I think we're getting, by George, I think we've got it. Okay, so what's the reactive intermediate here in this problem? A star. And that's the only concentration I don't know. So I write out R of A star. And what is R of A star equal to? What reactions is A star in? Okay, so I'm going to do the same thing. Go ahead.
A sub 2B.
And the coefficient? 1 minus 0. Good. See, notice how fussy I am. You could have said 1, but today I want to show me that you're looking at both alpha 1 and alpha 2. Eventually you'll just write 1 or minus 1, but it's always better to always write both numbers. Even though it sounds trivial, it's a way to not make a mistake.
Now we have to look for K2, which is
Yeah.
A star plus
A star, what was the other
A.
thing? AB,
And the coefficient is 0 minus 1.
0 minus 1. Good. Next.
So now you're looking for A star again.
Reaction 3.
You got AB times A2.
Huh? AB times AD, reaction 3.
Concentration of A star times to the 1 power times concentration of A2B.
And the coefficient?
0 minus 1.
0 minus 1. And finally,
For K4, AB times A2.
and the coefficient?
It's 0, no,
Coefficient's A star, remember?
1 minus 0.
1 minus 1. Okay, one thing I want you to notice, that was all very good. I want you to notice that whenever I have a reaction 1, it's always the same concentrations. Notice K1A2B, K1A2B. Reaction 2 is always the same. K2 ABA star, K2 ABA star. K3 A star A2B, K3 A star A2B. K4 A2AB, K4 A2AB. Because you're always just looking on the tail and doing the concentration part. What differs between here and here are the stoichiometric coefficients. So if you like a shortcut is, once you've done this, once you've figured this part out, for one reaction, it's the same for whenever you have that reaction contributing, the power product is always the same. The only thing that differs for different species is stoichiometry. Okay, so now let's notice something. The rate of a given reaction, the rate of this reaction, reaction 3, is A star A2B times K3. In other words, let me rewrite this. I'm not going to fuss too much about this, but this is equal to 0 minus 1 times the rate of reaction 1, plus 1 minus 0 times the rate of reaction 2, plus 0 minus 1 rate of reaction 3, plus 1 minus 0 the rate of reaction 4. And this one is equal to 1 minus 0 rate of reaction 1, plus 0 minus 1 rate of reaction 2, plus 0 minus 1 rate of reaction 3, plus 1 minus 0 rate of reaction 4. That is, R1, R2, R3, and R4 don't depend on stoichiometry. The rate of reaction 1, R2, R3, R4 don't matter which species I'm looking at. The rate of reaction 1 is always K1, A2B. The rate of reaction 2 is K2, AB, A star, etc. But when I'm looking at RA2B, I have to multiply that rate by a stoichiometric coefficient, by alpha 2 minus alpha 1. So the R1, R2, R3, R4 don't change from species to species. The only thing that changes is the stoichiometric coefficients. Okay, so let's notice, so this is a reactive intermediate. So what assumption do we make for reactive intermediates? What was I up to? Who was the last person?
I'm sitting over there.
Let's see here.
We assume that it's a static state
For which species?
for A star.
A star. So what does that mean about the rate?
That's
I can't hear you.
that's the intermediate of the reaction.
So reactive intermediate. So what does that tell us about the rate? What does it tell us about the rate? Do you remember what I told you the first day? Your purpose to be here is not to be a piece of furniture. We have enough furniture. We have enough chairs. We have enough tables. The purpose for being here is to listen and to learn. If you can't be bothered to pay attention, then you shouldn't be taking the class. You have to pay attention. And I'm asking, this last question, I'm asking you to repeat something that we said 5 minutes ago exactly. So if you don't know the answer to this, you're not paying attention. I'm not even saying understand. You're not paying attention. If you were paying attention and you didn't understand it, you would at least repeat what I just said. Okay. What does the pseudo-steady state assumption tell us about the rate of A?
Rate of A star is equal to 0.
It's approximately 0. Okay. This will not happen again? Is that clear? That won't happen again. I'll ask you to leave. If you don't pay attention, I'll ask you to leave. There's no reason to write. You can copy the notes from someone else. If it's too hard to write and think at the same time, don't write. It's most everything I'm saying is in the book anyway. If you can parallel process and write and think at the same time, that's fine. If you can't, then it's better to listen than to write. Okay, so let's now go through and try to analyze this. Again, I have two unknowns, the rate of A2B and A star. Everything else is known. And I have two equations. So I should be able to solve this. Now, in order to solve this, I could go through and do it the same way I did it here. But I want to minimize the algebra. Notice here I have 4 terms, and I'd have to plug in for A star in 2 places. But I can always add 0. If I add 0 to something, it doesn't change. You don't have to do it this way. It just makes the algebra a little easier. So I'm going to add these 2 equations. Because RA2B plus 0 is still RA2B. If I add them, then what happens? I have minus 1 and plus 1. Higher mathematics? 0. Plus 1 and minus 1? 0. Minus 1 and minus 1? Minus 2. So I have a minus 2, A3, A2B, A star. And then I have plus 1, plus 1, plus 2. See, I ask hard questions. K4, AB, A2. So that means when I solve for A star from here, I only have to plug in once instead of twice. If you like plugging in twice, go right ahead. The more algebra you do, the more likely it is to make mistakes. So now let's solve this equation. Again, both of these terms have an A star in it, and they both have a minus sign. So I bring them to the other side of the equation, I factor out the A star, and I'm left with A star is equal to. The 2 terms left on this side of the equation are K1 A2B plus K2 AB, plus K4 AB A2. So these 2 terms remain. I just recopied them and noted that 1 minus 0 is just 1. And these 2 terms went to the other side of the equation. I factored out the A star, and I divide what's left. So I have a K2 AB plus K3 A2B. Is that clear? And now what I'm going to do is I'm going to plug this into this equation. So I have R of A2B is equal to. So in the denominator, I'm going to have this thing. I've got a K2AB plus K3A2B. And now I have, okay, so I've got a 2 on the outside. Both of these terms have a 2, so I don't have to carry that with me. And now I've got a minus K3 A2B minus K3 A2B times A star. A star, so I have this thing. K1 A2B plus K4 AB A2. So what have I done so far? I've just written the first term, minus 2 K3 A2B times A star, which is all this. Just written the first term. Yes?
Question, there's two independent equations. Are you using the same equation? R2B is from that, right? Right.
I plugged into here.
Right.
This is the same redundant equation
And the A star you got from adding.
from this equation.
Alright, okay.
So equation 1, equation 2, equation 3 is 1 plus 2 equals 3. And this comes from equation 2 implies equation 4.
Okay.
And then this is 4 plugged into 3. Gives me 5. Okay. Okay, so now I plugged into this term, and now I need this term. So this term, there's a 2. There's an AB, I need a, where am I? K4 AB A2B. So I have a plus K4 AB A2. But now I want to put it under the same denominator. So I divide by the denominator, I multiply by the denominator. So I have a K2 AB plus K3 A2B. Is that algebra clear? It's trivial, the algebra. And now I put it under one denominator because things are going to cancel again. So I want you to notice that I've got a K3, K4, ABA2 with a minus sign. And here I have a K3, K4, let's see. I've got K3, K4, A2B, ABA2. K3, K4, A2B, ABA2. This one comes with a plus sign, this comes with a minus sign. So the K4 term here cancels the K3 term here. And I'm left with precisely 2 terms. Is that clear? Now, let's analyze this. Now let's go through the the experimental fact. The first experimental fact, again, is RA to B is independent of AB. Not the first, but it's the first one I want to use. So let's look at experimental fact 3. Experimental fact 3 tells me that nothing can depend on AB. Okay, well, I don't see any ABs here, but I do see an AB here. And I see an AB here, and an AB here. If I want to eliminate all those AB dependencies, I have to let K2 be 0. Because if I don't, if I just let K4 be 0, it eliminates these, but it leaves this. So I need to eliminate K2. So this tells me that K2 equals 0. I have no other choice. So what happens when K2 is 0? And I kill this, and I kill this term. I'm sorry, K2? No, K. Did I do that algebra right? K2. Yeah, I guess that looks okay. Yeah, that's fine. And I kill this. So notice, this term doesn't exist anymore. And what am I left with? I'm left with K3, A2B, K3, A2B. They cancel. So this cancels.
split out the second term of the numerator for the
It's canceled because K2 is 0. This was already 0, so this whole term is gone. Okay, so what this tells me is that the result now is minus 2 Ka2b. So this implies that Ra2b is equal to minus 2 K1A2b to the first power. And that clearly contradicts fact 2. That contradicts fact 2. So we're in trouble. We spent 45 minutes doing 2 mechanisms, none of which work. So now I need your help, because we need to come up with another mechanism that might actually work. So now it's your turn if you want. This is but although this is a volunteer question, this requires thinking. So we need another guess. You have first dibs if you want it. You want to come up with another guess for how to get from A to B to AB to AB and 1/2 A2. From 2 A to B's to 2 ABs and an A2. Volunteer for another guess?
Might be going to A, B, B.
What goes to AB?
In an initial reaction.
Initial, what's the reactant?
Right, gonna be A instead of being A2 is gonna be B2. We use the intermediate.
Wait. In order for me to understand what you're talking about, you have to say a reaction. The reactants are, the products are.
The reactants would be A, B2, going to.
There is no AB2. There's A2B.
I thought I would change the intermediate reactant.
You can change the intermediate, but you can't change the stoichiometry. You have to start out with this and end up with this. The question is how you get there. You can start out with twice this and end up with twice that. But you can't have new species and not have these. You can have new species in addition, but not instead. Volunteer? Tell me how. A to B gives what's the intermediate just from balancing the equation? E star. And then? Plus A2B. 2AB. It's worth a try. Let's give it a shot. Okay? So now I'm going to use this shorthand to make the writing simpler. Actually, I don't have to. So, yeah, let's use the shorthand. So I've got RA2B. Let's just go to the easy one. Well, A2B is involved in all 4 reactions. So I'm going to start writing that. And I'm going to have the reactive intermediate, E star, is also in all 4 reactions. So I'm going to have K1, K2, K3, plus K4. Okay, so first we're going to do this a little bit streamlined. I want to get the concentrations that go with K1, and I'll put them in both places. Concentrations that go with K2 in both places, etc. And then we'll go fill in and then we'll fill in the stoichiometry. So I think we're up to you now. Let's start with what concentrations go with K1?
A2B.
A2B.